Thank you very much for joining or for continuing this RIIAA event. This is the third year that we organize this. And we have the pleasure to present Eric Fiala. He's a part of IBM team in Canada. And Eric is a hands-on and AI machine learning, deep learning solution architect from IBM Spectrum Computing based in Calgary, Canada. He is seasoned system administrator specialized in distributed computing, big data, machine learning, and deep learning at scale. Eric works with clients to create resilient enterprise-class solutions to support today's and tomorrow's science. He has worked across a broad spectrum of industries, including oil and gas, finance, retail, automotive, and healthcare. Eric was an early adopter and proponent of Hadoop and related projects, and he has followed the evolution of these projects closely from the early days. Prior to working IBM, Eric was founded and managed several IT companies, web analytics, remote wireless surveillance, general IT companies, monitoring software, etc. He is recognized for us in IBM as a dominant expert. And Eric graduated from the University of Ottawa with a degree in economics, and he is fluent in French and English. Bonjour, Eli. Thank you.
Super. Thank you for the introduction, and thank you for having me here at the conference today. I had the pleasure of listening to some of the earlier talks, and I can definitely say that while we won't be going as deep in the science, we're definitely going to try to attempt in the next 23, 24 minutes to define the problem. What does it take to support a group of scientists, a group of users, whether it's in a company or in a research institute, to enable them to do science rather than work on redoing these science projects. Building an AI, building some data sources, building, getting TensorFlow installed, all this stuff that I feel. These smart people that talked earlier today, really, I want them to be doing science. I want them to be, stretching the bounds of some of this stuff. So very quickly, we'll define the problem as we see it. What does it take to move from science to meaningful science for the enterprise? What does that involve from a system and a software point of view? And then we'll introduce a few features that IBM helps to support gaps in this area. I'll skip through this stuff quickly, right? Everybody can understand or has their own definition of the difference between machine learning, deep learning, right? Key, I think, is complexity, right? The curve of complexity is increasing, kind of like the growth around, deep learning. I think the inception of TensorFlow 2011, PyTorch, that's that next dip. You're going to see a lot more of this as more frameworks come on board. The reality is that it's here, right? More advanced ways of science, more types of science that are leveraging some of this math that has existed for a long time, but has not had the accelerators, the compute power to make it feasible within an average lifetime, right? As I was presented, right, I work with a lot of different clients, and I like to use this slide to kind of break the ice, right? When you see large publications like The Economist, Forbes, etc., that say, hey, you're a big company, in 5 years, I think it was Elon Musk that said this, in 5 years, if you're not doing AI, you're not going to exist, right? A CEO might hear this kind of statement and think, oh, wow, I need AI right away, right? But really, for it to become meaningful science, we want to put science, like everybody was discussing today at this conference, into the hands of these business operators, as opposed to them using AI to do another example of dogs and cats, right? The difference of dogs and cats, or the exotic example of, zebras and horses, right? No, this isn't meaningful science using AI for meaningful science. And really, it's important to move in that phase from an innovate and inspire, right? If I take a bank, or if I take maybe a healthcare life science client, right? A lot of healthcare life science today in research organizations, right? Innovate and inspire is, okay, we're acknowledging the fact that maybe we can understand more how the brain works by investigating neural networks, or maybe we can understand how to cure infectious diseases more, right? That idea, how do we have that idea? Piloting, proving, just like piloting, improving a drug, that's when you're testing the idea, right? Validating your hypotheses, validating your theories. But for a business, until you move to the extreme right here, into the refine and repeat, right? Having a refined and repeatable process that's clean of privacy, clean of these ethic violations, et cetera, that are the reality of AI. AI for the enterprise really is just a science project, right? Our goal is to move people from this innovate and inspire, right? Acknowledge that yes, AI has value. AI can be infused into my business and bring value to it. Pilot and prove it to see that, okay, yes, through AI, I can inspect my fleet of vehicles more intelligently. I can provide better client or patient care, right? And then refining and repeating it, right? Putting it into a box and making it trustable, right? Making it repeatable and making it production ready. Right? Type of use cases that I see, since I work with a lot of finance, is stuff like this that we see on the screen. Right? This is a big bank. They're trying to use some RNNs to make predictions on the next tick of the stock market. Well, a few steps are important here, and yes, transformers are the new LSTM. So I don't think this slide says that LSTM, but I do know that much, at least, about the science. So, but nonetheless, right, a couple of key critical elements here, right? The speed of the data, right? We need the data quickly, and we need to be able to infer on that data as quickly as possible. Two, the validity of the model, right? Anybody can plug some numbers into a model, and it spits out some, number, right? On this, it's a binary condition, so 50%. Is your model better than 50%? Great. Is your model better than a human? Even better, right? But getting to that phase, a lot of pieces are involved in that, right? For me, being able to, maybe code this up in a Python notebook on your laptop, right? To be able to demo it, sure. But then linking this concept or this science with a team of 20 or hundreds of traders that are making active decisions. Important gap there, right? And one of those gaps revolves around this team sport, right? I heard a lot of collaboration in the talks earlier today, right? Collaboration, multiple people, multiple skill levels, right? You have people amalgamating the data. You have people coming up with a business idea. What are we going to solve today, right? Who do we want to help? And then this iterative process, if you notice, between the phases, and anybody who's done data science or has developed a model understands this. But it's even more explicit in business, because until you get to this, the magic money sign, or the magic, save lives sign, or the magic impact or meaningful sign, right? A lot of this is for naught. And it's through collaboration that we can get to this more efficiently, right? In more of an ordained manner, and more of a manner that fits with what the enterprise expects, right? I think that's the other expectation. To some CIOs, to some large business leaders, this is kind of scary, right? We're deep learning. I mean, this is AI, Terminator, right? No, we know that it's not. I mean, it could be, but no, I think this is there's legitimate use cases for AI and the value of AI in business today, and leveraging that's important. And again, kind of more of a drill down on the roles that we're dealing with in business, right? And paralleling this to research, I mean, your head of IT is there. Your line of business might be your research lead or department lead, right? And the data scientist, well, is you, right? All of you on the phone here working with the science. How do we build a system that quells all of these needs, all of these wants? And I think the importance of balance is necessary to underline here, right? I think three keys to the balance is, one, around having a big engine, right? You want to have accelerators, so we call out GPUs. GPUs are cool, they're hip. We call it FPGAs, system on chips, etc. Right? As science increases, I'm sure there'll be other types of accelerated technologies that bring us to this glory. And just like a race car, to continue the analogy, big fuel, right? Without fuel, that race car is going to look good parked and is not really going to go fast, right? And most importantly, without the fuel or the engine, right? Forgive me, I'm not an F1 fan, but maybe if you're Verstappen, right? The data scientist here, Max Verstappen, without the engine and without the fuel, some will argue that his car isn't going to do much, right? So between the scientist and the science, right, these complex algorithms that have often been sitting on shelves for years, right? I saw a lot of good references to papers from the 60s and 70s in some of the earlier talks today. I mean, this stuff has been there, but what's been lacking is these engines and this fuel and the coordination of all these pieces with a common theme to be able to reach these exciting conclusions, right? So topology matters, right? Again, we know that the weakest link or the slowest link is going to determine the speed of your pipeline. And this is just one example, right? Where there's a lot of different pieces involved, the chain pipeline, multiple learners. Well, in this case, the speed of my slowest learner is going to determine the speed of my whole pipeline. Right? Is this acceptable? Is this a value or an efficient use of resources? Maybe not, right? As a researcher, is this something I want to be thinking about? Some would argue maybe not, right? Maybe I'm not a distributed computing expert. Maybe I'm not somebody who has done hyper-performance computing. I understand the science, I understand the math. I just want this to run fast. I want something that took days or years to be run in hours or minutes. And a lot of that is important. I think that this chart here sums it up pretty well, where you have a large emphasis that's happening today on the ML code, right, the machine learning code. And that's cool, right? A new algorithm comes out, a new library comes out. I think that's neat, right? I think there was a question around GPT-3 and BERT and all these other models from earlier sessions. I think, yeah, that's neat. I read the articles, great. Science is advanced. But to me, again, making this ready for the enterprise or meaningful, right, as meaningful science, all this we want to have it set up before, right? The configuration, the monitoring, the serving infrastructure, right, the data verification. All this is what makes the ML code seamlessly be able to run in a team environment where multiple users are collaborating. A couple more points I want to make before we dive into a few things. One is around use cases, right? A lot of the use cases I heard today were around healthcare life science. I thought, that's definitely an important area right now. And as a few of the presenters said, it's, I believe, an area that's ripe for people to, bring their science to the domain and grow healthcare life science and deep learning. Yes. Now, I think another point I'd like to make is that a lot of people look at it in an industry point of view. Oh, I'm a finance specialist. I'm a healthcare life science specialist. I must stay contained within my industry or whatnot. But I like to look at these AI use cases more in a function point of view, right? Stuff like, customer interaction, stuff like computer vision, right? Whether you're looking at a hippocampus or looking at, somebody's social distancing in a social setting, or, a factory looking at production quality. All those are vision problems, right? And all those are common and can use very common concepts between them, which is, food for thought or something to, take into consideration. Finally, I have another slide that's really bring us back to the point that while deep learning is new, new to some, new to many, or at least, not many decades in the enterprise, right? If I take a generic stack that looks like this, take off the word AI, and remove the machine and deep learning libraries and frameworks, what I'm looking at here is very much the same thing in the enterprise that I needed to, do traditional HPC, to do SOA-based workload or client-server-based workload, or even Hadoop or big data-based workload, right? A lot of this doesn't change. We still need high-powered servers, some storage, some sort of amalgamation of that storage, a way to distribute that workload between one machine and another machine in a seamless way. And only when we get into the different specific libraries does, oh, okay, deep learning is different. Yes, we're hosting something different, but having that solid foundation is essential to success, right? To success in doing things like this, right? We look at this, a basic machine learning workload or deep learning workload where you're ingesting from data sources, preparing your data, right? Doing hyperparameter optimization, monitoring the workload as it's coming through, training, doing that at scale, and finally being able to inference. Doing all this in a multi-tenant setting is, another element of importance, right? How do two people collaborate with a limited set of resources? essentially what people want, or what we see in the field, is something like this, right? We have a pool of resources. We have a set of different users that are dynamically pulling from these resources, in this case, these expensive GPUs, and doing this in a way that's very much synonymous with how we've done stuff in grid, and applying some of the science on top of that to enable easy distributed computing with the focus on GPUs. For those of you that are still at the point where you're doing this on your laptop, that you're not doing this in a grid setting or in the enterprise with hundreds of different users, some of this might be lost on you. But I as a sysadmin or as a provider of a grid, a deep learning as a service grid, I want your experience to be as simple or as easy as it is on your laptop. But I want you to gain the value of having multiple machines, a managed environment, and being able to concentrate on the science right away. Okay, so a couple of good points. I feel, I brought them up, of course. I'm going to agree with myself. Hopefully some of you agree with some of these points, or at least kind of consider them if you're building out AI grids or deep learning as a service, or capabilities maybe attaching to current HPC grids and understanding how to do it. I'll quickly go through a few things that IBM does as far as AI, right? We have servers. Our servers are fast. Our servers are purpose-built for AI, to the point where Summit and Sierra, two of the most powerful computers in the world, are using these. So some people will say, okay, well that's a lot of nodes. I'm a small company in Mexico City. I don't need 4,000 nodes. I need 2 or 10 or 15 nodes. And that's the beauty of a system like this, is that it scales nicely, right? It's a small footprint that scales very nicely and sits alongside a family of other hardware products that are specialized around either the data side of the equation, the training side, or the inference side. So really having purpose-built machines for the different tasks, I think, becomes important, and maybe that second level consideration, right? Costs. If everyone had an infinite budget, obviously we would all buy the best and most expensive. But with a limited budget, we want to deal with the best tools for the right job, and I think that's definitely important, right? IBM also provides a set of Conda libraries, optimized, right? That provide an easy way, Conda install, TensorFlow, Conda install, PyTorch, etc. Do this on x86 platform or standard Intel platform or IBM's Power platform. So definitely interesting. Definitely invite you to have a look at it. And I'll talk in a couple slides about one of the libraries that comes out of there, SnapML, which is some of the research that we're trying to push towards the forefront, giving back to the community what we can do. Something else that we have a lot of focus around is hyperparameter optimization, right? In the simplest sense, think of a series of embedded for loops, right? For this value of base learning, for this value of momentum, for this value of Nesterov, find me the most optimal set of hyperparameters. Well, in the simplest sense, chain those jobs, run one at a time on your GPU, and yeah, you could run those, right? But now we're in a shared grid with multiple users, and you also have access to multiple machines, multiple GPUs. So how do you do that most efficiently? We provide some tools around that, right? We provide both algorithms for quicker search, as well as pluggability of your own algorithm, but also a kind of running that distributive layer in my generic graph to distribute some of this workload, right? So now the scientist is no longer thinking, okay, so I want to tune for these parameters. I want to put this tuning on this machine, and then, okay, I can borrow this machine from Jose because he's not using it today, and I can borrow Maria's machine as well, but they'll be back tomorrow. So I can only, it gets complex, right? Why are we making stuff so complex? Or why are we saying, okay, data scientist, here's your box, right? Here's your big server, you can have your server, nobody else is going to share it. And I come from that world of grid computing where this is just, to me, it's absurd, right? Together we make progress, I think is how we can sum that up. And auto hyperparameter tuning is just one of those ways that we can facilitate that. Another one is around distribution, right? So we're facilitating that distribution. So now I have my model, it runs in 30 hours on one GPU. I want to run it in 1 hour, right? Or I want to do several iterations of it, more faster, more better, or have a larger data set or something. We provide several tools around that. One is around supporting native distribution engines, right? So your standard distributed TensorFlow, Tachyon, Spark, etc. We support that. One is around a library that might make sense to some people in the HPC world. It's called DDL, right? It's an all-reduced library. It leverages MPI for distributing and passing gradients and whatnot. Very, very good, but as the note implies here, definitely a single user workload, right? So if you want to have a big workload and you want to say, okay, I want to use this GPU and that GPU, set up your rank, etc., it's great, right? But in a multi-tenant environment, really, I think key is elasticity and dynamic, right? We know that the usage is going to change. We know that we want to have that elasticity, right? And maybe the user, a pattern of saying, hey, I want N number of GPUs might be simpler for a user rather than thinking in distributive terms and passing that task down to the user, right? So definitely things to consider and definitely important pieces. For any comments around, oh, this sounds interesting, but is this a closed system? No, I mean, the good idea is, or the good news is that we have something called Bring Your Own Framework, right? Bring Your Own Framework is really a wrapper around your libraries or the frameworks that we don't support that bring the value of the resource scheduler to that framework or workload. What does this mean? Well, it means a few things, right? If we talk about elastic distributed training in a multi-tenant environment, right? This is different workloads. Each different color is showing. The graph's not showing up too well, but you can maybe imagine. But each color is showing a different a set of workload, right? The pink or the red is 16 different users requesting 4 GPUs at once, whereas the blue is 8 users requesting 8. And you can see the plus minus overhead of these multi-tenants sharing in a dynamic manner on the grid is plus or minus 2%, which is pretty incredible. But also the scalability, right? So near linear scalability. So that at a case of 1 GPU 30 hours, 30 GPUs, well, pretty darn close to 30 hours or to 1 hour, which is kind of cool. It also opens up the possibility of scenarios such as this, right? Where you have job 1 that starts at T0, job 2 requesting 8 GPUs, job 2 that starts at T1 requesting 8 GPUs as well. The fair share that kicks in that not only balances the resources, but also formulates the shape of the neural network to accommodate for the number of iterations that have to be done on that initial input layer. It's pretty powerful, a lot of words. I'm kind of speeding through it, but definitely speaks to the breadth of IBM's portfolio in AI, right? After we beat Kasparov, and after the Jeopardy, we continued doing AI, right? We didn't just fall asleep. SnapML, another library, right? That we're moving traditional ML stuff, regressions, GDMs, decision trees, etc., onto the GPU, right? We're seeing some pretty wild increases in speed as a result. 46x might be a good marketing number, but more realistically, 12x's, 20x's, etc. It's huge and it's big, and that's what the enterprise wants in order to be able to take that risk to say, hey, yes, I'm going to take AI, I'm going to try to use AI in a process and make the business process more efficient and more valuable to me, the business owner, right? Other tools that we have are around more visual identification and more geared towards the subject matter expert, right? Somebody that can click on a box, identify a defect in production, identify a car versus a crossway, etc., and then building a maybe more simplistic model, but maybe a model that's good enough in order to deploy and use AI. Right? The same capability exists in a mobile version with a mobile app. You see it here on a manufacturing floor, and definitely a great example of using AI, not just in the data center, but on the edge as well. So very interesting and important. And I see there's 3 minutes left here. I don't know if there's any questions that we should address. See a few questions in Spanish. And Spanish is not that good, poquito. But 2 last slides I'd like for us to consider. And one is around leveraging multiple different types of tools for multiple different types of users depending on the application. That means from the line of business user all the way to the smart data scientists, like the users that have been on the phone today or on the conference today. Right? We need to support in a business setting all of these users. Somebody who's used to using an Excel spreadsheet all the way to somebody who's used to writing the next TensorFlow. And for that, we have a great platform under the title of Cloud Pak for Data, right, which attempts to address all that. And again, the openness is throughout, right? We build to run on any cloud, any platform on premise using OpenShift, supporting some of these functions around collecting data, organizing it in a common platform, and finally being able to analyze or infuse all of this great stuff that you have on your platform in a common platform that fits within the enterprise. So it doesn't omit important enterprise capabilities such as authentication, authorization, encryption, and all these other we'll say words that sometimes might slow down science, but are definitely necessary in the enterprise setting. So I think with that, I leave you with the thought of, business owners, or maybe those of you still in the wing of research or university, how will you get to meaningful science today? And hopefully some of that will be, jump into the science today, start doing science today, meaningful science, and spend less time trying to rebuild what a lot of other people have built. So with that, thank you. And I'd like to thank Synergia as well, our partner for this. Thank you.
Thank you so much, Eric. Let me check if we have some questions. At least I have one. I think all these features that you already show, I don't know if somebody else has something, especially something equal to this, not something equal to distributed deep learning or something like that. No, I think the things that IBM has been done with how the memory is shared is different for everybody, in the world.
Yeah, definitely. I think that IBM being a large company, we do well in having good pockets of excessively deep science, right? I think the feature you're talking about is Unified Memory Bus, which allows us to swap tensors in and out with our large memory support library using the system memory, which is super powerful, right? Now it's no longer a 16 or 32 gig GPU or whatever your department could afford. It's 16 and 32 gigs plus that terabyte of memory you have on there. Like, wow, that's mind blowing, right? SnapML, these 10x's, 12x's. Again, it's mind blowing, and the amalgamation of all this under one common banner is, to me, for a business, a good value proposition, right? Everything from servers to software to support of that software to access to IBM's research, right? I mean, today we're talking deep learning and AI. IBM's already diving into quantum and other next generation compute methods, we'll say. Whether that becomes enterprise ready today, tomorrow, or in 10 years, I guess we can all bet on that. But I think deep learning and AI is here today, and teams of data scientists need to be enabled to do some of this.
We have two questions. One from Jason Angel. He said, what are the most relevant technical skills do you think a deep learning engineer should have for working on big data scenario?
Yeah, that's a good question. And frankly, I saw some of the science today, and the science is way above what the enterprise is requiring, right? I'll give you all that, right? Basic skills are important. I can talk for myself that at least in North America, I've been able to advance in this field and pretend like I know some of this deep learning simply because I can communicate some of it, right? Now, communicating it means that you have some basic skills, right? Basic data science skills, right? Come with strong Python, come with strong R skills, understand the math behind some of this. Finally, and I think in the introduction they said I was an economist, I studied econometrics, and finally, some of the math that I learned in there is being, valuable in some of this for me to understand the concept. So, the basics are important. All this super deep stuff is super important, but to make it relevant to the business, sometimes, the basics are really the most important bits. So, good question.
Another question from Oscar. He has two, but only one. Do we have an internship for machine learning? Do you know any program from internship in IBM?
Yeah, I'd invite anybody that's looking for an internship to investigate either the Summit program or through IBM Research. If you look at the IBM Research site, we have various different collaborations. One I've been able to work with is the Satori cluster at MIT. pretty cool. Goal was to build out a deep learning as a service for users, and turned out it was the 4th greenest computer in the world. So that also becomes relevant, right? How many, what is your economic or your environmental footprint to the deep learning that you're doing, and how can you lessen that? And I think that's another area that's fairly rife for research. So definitely interesting.
Okay, due to time, we have to close, but we have more questions. Grecia, Gabriela, please contact me. I'm sending the email. Please contact me, and I will contact Eric. Thank you so much, Eric, for your presentation.
Yeah, thank you very much, everybody. And have a great day.